Welcome everyone, and thanks for joining us this afternoon for today's webinar on FE model updating with FEMtools and with applications to satellite technology. This is part 2 of our webinar series on test correlation, sensitivity, and model updating. So if you missed the first part, it's still no issue. There will be a brief recap during the presentation. My name is Kelvin Bwedi. I'm a technical consultant at Insuma and also today's moderator. And today I'm joined by Eddie Despot, CEO and owner of Dynamic Design Solutions, and also the main presenter of today's topic. So here we have a brief overview. So we start with some introduction, and then we'll move on to sensitivity, and then also FE model updating, some demo also on the P200 SDM satellite delivered to us by Redwire. And then we'll finish it off with some summary and some conclusions. Next slide, please. Before I hand over to Eddie, I would like to briefly introduce Insuma Innovation, the organizer of today's webinar. So we are the exclusive business partner of Hexagon in the Benelux, so Belgium, Netherlands, Luxembourg. And for those in the FEA world who are not familiar with Hexagon, perhaps you are familiar with the name MSC Software. And we offer simulation tools in different physics domains. So for instance, we have the structures and durability, where we have legacy tools such as MSC Nastran, Patran, MSC Mark, and so on. But we also have different domains, tools in different domains, such as in acoustics, where we have Actran, computational materials, thermal and fluids, virtual manufacturing, where we have tools for welding simulations, forming, additive manufacturing, and so on. So that's just a brief overview of who we are as Insuma and also Hexagon. And with that, I will hand over to Eddie to continue with the presentation.
Okay, thanks, Kelvin, and welcome joining us this afternoon for part 2 of our webinar series on this application of FEMtools on the Redwire satellite. So Dynamic Design Solution is a CE company located in Leuven, specializing in this kind of activities. So meaning the integration between FE simulation and test data, mainly for the purpose of validating and updating a finite element model. So for this purpose, we developed FEMtools, which is a family of modules that are built upon a framework that has interfaces, graphics, scripting capabilities, database management capability. And on top of this framework, we will then offer toolboxes for dynamic simulation, for test planning and correlation, updating, optimization, and also specialized add-ons. So the application that we talked about it in previous webinars was test planning. And so here the next slides show a bit where this is positioned in the workflow. So as soon as we have an FE model available, a baseline FE model, then it can be used to simulate and optimize a test configuration. So okay, here it's called modal test planning because we will in this presentation mainly talk about the modal-based approach, but it can also be in statics analysis or in using frequency response analysis or operational deflection shapes. So there can be other types of simulation that are involved, but I think the modal-based is most popular one. So in this slide, we show the modal-based process. And so this baseline FE model can really be useful to help the test engineers to define the test setup in terms of the sensor locations, excitation, shaker locations, support locations, and so on. Next slide shows the correlation task, which comes into the picture as soon as the test has been performed, and we have now FE data and test data that can be compared. So in brief, it is about finding the differences and the similarities between the simulation and the test data, and then also creating like relation tables or pairing tables, as we call them, where in the modal approach, the final result there is the modal pairing table or the mode-shape pairing table, which is essential information to allow us to determine what is the distance between the two data sets. What is the gap that we need to close by updating the model? So this is in the next slide, which is the topic for today's webinar. So assuming there is a gap to close, I think it's in practice very exceptional that correlation analysis would be satisfactory from the first round. But so the correlation can be improved by means of modifying input data to the FE model. So we call those updating parameters, and our targets we will call updating responses. So what are the data, the response data in terms of frequency, modal displacement, but also mass, for example, can be considered like a response, which means it's something that can be measured and serves as a target for the simulation. So for these responses, we will identify parameters that can modify the response in simulation, and then the modification that we need is then what we call the residue. It's the difference between the target response, the test data, and the simulation. And so sensitivity analysis will help us finding parameters that can do that, for which the responses are sensitive, and then the updating task will allow us to find what is the necessary change of the parameters. So this is in brief what model updating is about, and it can serve different applications like validation of modeling assumptions. As we are doing this in the modal domain, it's a very, very important domain because it's the industrial approach to frequency and time domain super response analysis by using modal superposition technique. So the modal base is actually the basis for the response simulation. So it is logical that we validate that modal base before continuing. It can be used for creating reduced component models that are validated when they will be added in an assembled structure. Identification of properties like material properties, damping, and so on. We can use, instead of test data, we can also use reference responses from a reference FE model, say a high fidelity model, a very refined model, and then update a coarse model. So this is a very common industrial application to create simplified models from a very detailed one, which is very heavy for computation. So big data sets, long computation times, where a coarsened model is much more practical. So the application that we will show today mainly will be the exploratory model updating application, which is actually in the case where you have not a very clear idea of what is the parameter to be updated, which is a key information or a key decision, then we can try a lot of parameters and actually update element by element. So in this case that we will talk about today, this means hundreds of thousands of parameters. And because of the specific features of FEMtools to handle such a large amount of parameters in terms of the speed of computing gradients, and also using this massive amount of parameters in updating, we can use that to find areas where selection of parameters would make sense. I mean, it is to find patterns, to find areas that stick out. And as you will see later on, this is what we tried in the satellite model that we worked with. Model updating, so all these applications that are specific applications of updating, but updating can also be part of an integrated solution, which is nowadays becoming more and more important, like the development of digital twins that are used in structural health monitoring or damage identification, for example. FEMtools is based on a framework that has built-in scripting and an API, a function library. So it's also possible to extend, customize, and develop custom solutions by means of that scripting environment. So would you need software to validate a simulation model? Well, it depends. If you have a case like shown here on the slide, like a cantilever beam that is bending as a result of a static load, you have the response may be simply the displacement of that tip, so that is one number, one model, and your variable may be the clamping stiffness or the material property, the elastic modulus. So that's a case where you probably can get away with just a trial and error approach, or making manual changes. But in case where you have like in the modal domain, you can have hundreds of modes, global modes, local modes. You have hundreds of sensors placed on the structure, different types of sensors, strain, displacement, accelerometers, and you have many joints, materials, you have local coordinate systems, and then you have a simulation that does not match the test. And you have no idea what could be wrong with the model. And there are thousands, if not 100,000 of potential parameters. I think that's a case where you need a specialized software like FEMtools to help you to be productive. And we have a similar case here at hand, and it is a demonstration also that you can really get a nicely correlated model in matter of hours instead of weeks or months of manual labor. So when we talk about updating parameters, I think I first have to clarify what kind of parameters that would be. This is mainly the physical parameters, material stiffness, stiffness of joints, geometry like plate thickness, for example, or beam cross-section. So, I mean, parameters for which there is a relationship between the response and the parameter. We know that the resonance frequency is a function of stiffness, mass, damping. So we have a relationship, and so that relationship can be used to compute gradients. And if we have gradients, we can use an optimizer. We can use optimization technology to find the parameter modifications that we require. Now, of course, we choose these parameters because we have uncertainties associated to them. But it can be that there is other sources of uncertainty and variability, like the model itself, the number of elements, the type of elements. We can also have like mistakes in the data. The solution parameters, like, well, simply the assumption that the structure behaves linear, is like can be kind of like a practical assumption. We have manufacturing tolerances, which is something that we know will impact the structure that we test. They may be variable from one to another because of tolerances. So we are testing such a structure. So it means that you test 10 different products and they may have slightly different responses. And then maybe also in surface variations like temperature or humidity that can have an impact on the response of the structure. So these are all kind of uncertainties that we have to be aware of, but that are not necessarily incorporated in the FE model, and so we have no control over them as a parameter. So in the automated updating that we will talk about today, we will limit ourselves to these that are shown the slide as being physical properties. I also mentioned that there is other types of model than modal approach. So we have the mass evaluation, the static approach, the frequency response, and the operational. So the modal is certainly the most popular because it is a very convenient type of data. I mean, we have very accurate ways to determine what the resonant frequencies are. It can be done relatively fast and inexpensive compared to other types of testing. Also, the frequencies that we obtain are function of stiffness and mass, which can be a benefit because you have more parameters that you can validate. Can also be a disadvantage because you may not be able to decide whether the change will be made in terms of stiffness or in terms of mass. So it's always useful to combine modal approach with either the mass or the static. So more practical will be the mass, and this is also what we do with the case study that we'll demonstrate today. So we have the modal approach, but we also will look at the mass, whether it will be required to also include mass parameters, meaning parameters that can change the mass of the structure or the center of gravity of the structure. If you want also to identify damping, you will have to include frequency response information where we have functions and we see what the amplitudes are at resonance. So that is then information that we can exploit to determine what the damping is in the structure. And then finally, also force can be considered a type of variable. If you don't know the force, then by looking at the operational shapes, we can use an inverse approach to determine what is the forces that caused the specific deformation. The next slides are a bit theoretical part of the updating. I will go very fast over these. So we determine what is the residue. So what is the difference between experiment and test with index E and A. So here for frequency. So this is what needs to be minimized. And we use a linearized Taylor expansion. So using the linear gradient, how much the frequency change for a parameter change. And then the unknown is the parameter change. So we can create these expressions for whatever responses that you want to include. So here it is with the modal displacements. Here we include the MAC, which is a measure of modal correlation, and we can also include orthogonality. So this is our base equation. So we are assuming a linear relationship between parameter and response, which in reality is nonlinear. So this means we will need an iterative approach. The computation of the sensitivities is done either in an analytical way, if we know an expression that relates the response and the parameter. As you can see here, it also comes down to knowing how the mass, damping, and stiffness depends on the parameter. If we don't know that relationship, then we can use a numerical derivation or a finite difference approach where we perturb the parameter and then we compute the response before After change can be done at the response level like a frequency, but can also be done to derive the matrices. So like here you see what is the derivation of the mass matrix or the derivation of the stiffness matrix can be done in an analytical or in a finite difference way. So this leads to 4 approaches, as you can see. These are all included in FEMtools, and the fastest computational method will automatically be chosen by the software. When it comes to the updating objective function, we are going to define an objective function which actually originates from looking at the test data as a point cloud because of the uncertainty in the test data. We will try to match that with a simulation point cloud, here marked with FEA, and bring those 2 point clouds together. So it means it's not only about the center of the point cloud, but also the size and the shape of the point clouds. This distance is in literature is called the Mahalanobis distance, and it's an extension of the Euclidean distance by including the inverse of the covariance matrices for response and parameter. So this brings in statistical information about the point clouds. Of course, there may be practical situations where you do not know what the point cloud is, then we will make assumptions about these statistics, I would say. So we therefore introduce what we call a scatter value, which is an estimation of the size of the point cloud. And with this scatter value, a user can express its confidence in the measurement or in the parameter values in the FE model. So what is the uncertainty depending on the level of simplification, approximations, experience. So this way, a user can control the results by bringing in this background information. This is quite essential, and it's also a very specific feature of the model updating objective function, and is what makes it different from a classic optimization problem, for example. And so this statistical concepts actually is what causes why we call this approach the Bayesian formulation. So Bayesian, which is maybe known for the Bayesian inference theory, so is also partially used in this approach. So the updating then itself is an iterative process. As you can see here, we will start by defining the problem in terms of parameters and responses, then correlate sensitivity analysis, estimate the parameters using the Bayesian estimator, update the database, means we have to go through the solver again, can be our internal solver or external solver, as we are doing in this demonstration project. We're using the Nastran solver, and then we come back with results to check the new correlation level, and then either conclude about the correlation is satisfactory, and then we can stop the process, or we have to continue additional iterations. In terms of sensitivity analysis and the choice of parameters, I think I want to at least, there's a lot of things to say about it, but I think what is most important is the choice between local and global parameters. A local parameter is a change at the level of the element. So I mean, you have a parameter for each element, and in this way you can also see sensitivity localized to the level of the element. A global parameter is a scale factor for a group of elements, and that group can be 2 elements. I mean, that the smallest group consists of 2 elements. The largest possible group consists of the entire FE model. So that would be like a global parameter that is a scale factor to the entire system stiffness matrix or mass matrix. So we can have an infinite number of choices between, at one extreme, global scale factor to the system mass and stiffness, or at the other extreme, element by element updating. Some elements will have multiple parameters that you can select. You can select elastic modulus, rho. You can select plate thickness. So there are different possibilities. So, I mean, you can have a huge number of parameters, function of the number of elements, and then go down to only one or two global scale factors. So, and then anything in between, depending on how you group elements. So that is the power of the software to allow you to easily work with all those possible combinations and try out grouping based on material, grouping based on geometry, on position, or components of the structure. So there are a lot of possibilities. On the downside of all that flexibility is, of course, that the challenge becomes to make decisions in terms of the parameter selection. So here is a simple example showing a plate structure. It's actually part of a hard disk. You see we have a correlation in terms of shape that is not that great. We have only a few modes. Here we see the frequency correlation. Ideally, we should be on the dashed line. So we have differences between FE and test frequencies. And here we have an overlay of the mode shapes with indication of the measurement. So the FE model here is reduced to the same model as a test model for a clear visualization. Now, after updating, we see we have the frequency correlation is perfect. We have nice convergence, meaning the objective function is minimized. We're almost at complete correlation. Also in terms of mode shape, we have nice correlation. And then here, using an element by element updating, we have a color plot that shows us the locations where we need to increase the stiffness or the parameter, and it's not actually stiff, it's thickness. So it's actually both stiffness and mass at the same time, because thickness changes both stiffness and mass. So here we can then visualize and localize what amount of change we need to the structure. So this is not a final result. This is what we call exploratory model updating, just to help you understand and get insight in the structure to find out where you need change of stiffness, in this case, true thickness or mass. And then in the next round, you will interpret the result to, if necessary, interpret and relate this to more physical changes if that is required. So this is the frequency value. So you see here the mode pair table before updating of this example. We have differences in terms of frequencies that are -18, which is an underestimation of the frequency, as well as +22, which is an overestimation. So this is challenging because it's not about a global scale factor that we need. We need for some modes we need to increase the frequency. For some we have to reduce. So this really indicates we need to make local changes, and this is very challenging for large complex structures because you have so many possibilities to find out what local changes are necessary. It's also interesting to see that for some mode we have already satisfactory correlation. So here for this mode we should not touch the model. It's already predicting the frequency very well. So this can be difficult, and the difficulty will increase with the number of modes, obviously. And so this is where the software is really showing its full power to working with a lot of parameters, finding you the optimal changes, again, and giving you an indication of what may be necessary in terms of change. This is another example applied to an engine housing. So again, we can highlight the areas that need refinement in this case. So indicating to the modeler where they need to investigate the model and check what could be how it could be improved. And the blue areas are not of interest. It's mainly the yellow, green, red areas that should be investigated. Okay, we have here a number of customer projects from Augusta, GPL in the US, Dutch base, FEO, where we have gone through similar approaches to demonstrate this workflow. So, I mean, we have applied the software in all kinds of situations for all kinds of industries. And so it may be that with the modal approach, you will need additional features like FRF based or ODS focusing on damping, on geometry. And like here you see that the difference between the FE model and the true structure is actually also because of the geometry that has been modified by the manufacturing process. In this case, cast iron that caused some deformation in the geometry. Combining different models, different physics, for example, static test with modal test, and then combine all the responses. So using super elements, using strain data, using full field data, like on this blade, where you see the result of a scan test that is then projected front of the FE model of the blade. So these are all kind of more advanced concepts that have been used in industrial applications working with our customers, but okay, we'll not be talking about those today, maybe at future opportunities. So we're focusing on the modal approach, where frequency clearly is the main response, but also the mode shape itself is a target. So the test data provides mode shapes, and we will of course try to, in terms of the MAC or the orthogonality criteria, try to improve the correlation. A unique feature of FEMtools is that we can also include the off-diagonal terms, so they should go down to 0, and that I think is interesting to include those additional responses, because I mean we can benefit from having more responses. So this is a recent extension of the software, so that's why I wanted to highlight it here. For damping, we can use transfer functions, as I mentioned, and then we will do this in a two-step approach. First, to match the peaks, and in a second, we will match the damping. So this brings us to considerations for defining the updating problem. Well, we will have to think about what parameters to update, and we will have to also know what is the purpose of the FE model, to decide whether we want physical change or mathematical change. What is the uncertainty in terms of the parameters? What are the assumptions, simplifications? So that's a bit related to uncertainty. Do we need local or global changes, which can be decided from how the correlation looks like, from one mode to another? Whether we need stiffness mass, whether we have background information that we can use, whether we can automate the process. I mean, a small change of parameters can be automated, but you cannot replace a rigid spring connection, which is infinitely stiff. You cannot replace that automatically by a very loose spring, because then we would have to you have to allow for a very large range of parameter values, or even worse, you can have like an RBE or MPC, which is a rigid connection where there is no physical property to update. So you will first have to manually replace that by a spring. So yeah, we have certainly a challenge here to make all these kind of decisions. The software helps you to do so by the sensitivity analysis tool, and the concept of explorative sensitivity analysis and updating, where we can select a lot of parameters and then look at these color plots, update with a lot of parameters, and then see if there is any trends. And so I have here a few examples where you can see there either a sensitivity or a result of updating, where you then can see, well, green, like in the middle example, green is zero change, and all the change is in those localized areas, which you can then interpret. In this case, it could be related to damage caused by stamping the holes into that plate. Okay, that brings us to the case study for today, which is the P200 satellite from Redwire. So this was introduced last time by Kelvin in the presentation on correlation analysis. So I will be very brief about this. And this was also discussed in the FE model, the different components, mean the base, the connection to the shaker, the interface ring. We have now in this plot I removed the front plate so we can see inside. We have there a tank, which is in this case not included as a shell structure, but as a lump mass, which is connected to a ring by RBEs. We have payload, we have solar panels left, right, and also at the back, which is a fixed one, and on the sides we have folded ones. So in the webinar of October 9th, we showed the pretest activities, computing effective mass, checking the sensor locations which were imposed. I mean, the test is already done, so we just wanted to double check those selections, if they were a good choice. We processed the test data, the FRFs, coming from the test lab. We extracted the mode shapes, and then we compared with the simulation. So that was where we left it last time. So now we will continue with the sensitivity and analysis. So we will have to make decisions about parameters response, mass modeling, do an explorative approach, updating, and then evaluate the results. So to recap from last time, we computed the effective mass, and this is important because, well, we wanted to include the modes with the highest effective mass. And in this case, so it was decided also with communication with the customer that in this case the validation should be checked for the first 5 modes, which is up to 100 hertz, or 118, but this is the simulation. The test data actually has frequencies up to 100 hertz. So then we compared those frequencies, simulation frequencies with the test. So here is the test. You see the largest is 90 hertz, where here it is 118. We have 2 global modes, tilting of the structure. We have 1 local mode of the fixed solar panel, and we have 2 local modes of the tank on the inside of the satellite. So I mean, this is 3 types of modes: global, a very local panel mode, and a local mode of only the part, the tank itself and its attachment to the base. All higher modes are mainly local solar panel modes, which are not considered in this project. We checked the correlation in terms of 3 criteria: model assurance criteria, the orthogonality check, and then POC, which is a pseudo orthogonality check, is actually an approximation of the orthogonality, which is very fast to compute, whereas the orthogonality itself can be time consuming because it includes a Gaussian reduction of the stiffness matrix, whereas the POC is only a vector criterion. So this takes seconds, while this in this case takes minutes. So it's an approximation that allows us to speed up the analysis. And as you can see, the conclusions in terms of correlation, mainly for the modes of interest, is the same. So this brings us to the mode pair table, and I highlighted here the frequencies and the differences that are of interest. So we see -8%, -3 for the 2 global modes, then -15 for the local solar panel mode, and then we have +21 and +30 for the local tank modes. So again, this indicates that we will need local changes, and we will not be able to improve this with a global scaling of stiffness and mass. Next, we check the mass from information provided by the customer that the structure was measured and weighing 320 kilograms. The simulation says it is 321. So this is close enough. So indicates that the mass is okay. And then for the center of gravity, we have information about parts of the structure, not the entire assembly. So this is without interface ring and no payload, but here also the differences between CAD measured and simulation are small enough to be acceptable, and the conclusion that mass modeling is satisfactory, and we will not have to include mass parameters, but also we need to avoid mass parameters, because otherwise we will start to change something that is already good. So this means our updating parameters have to be stiffness only. So obviously, knowing that there is a lot of springs in here, we start by looking at spring, and you can see here a sensitivity analysis for local spring stiffness. Clearly for the tank modes, you can see here we have clearly sensitivity for at the connection with the base plate. For the global mode, the connection with the satellite with the interface with the shaker table, and for the fixed solar panel, we have also high sensitivity for springs connecting it to the satellite box. So this could be like a good starting point. There is, however, something to be considered about spring stiffnesses and updating, which can be tricky, which is something we call saturation. You see that this is a relationship between frequencies and stiffness, not necessarily for this structure, but it's more general, where we see that at high stiffness value, the sensitivity becomes very, very small. And it means changing the parameter in this case does not change the frequency. So it means if a stiffness is very high, it becomes actually impossible or very difficult to update it because of the low sensitivity. At the low end, where the spring is very soft, the impact of stiffness changes can be very high. I mean, consider a structure that is free or is constrained, the mode shapes will change dramatically. So making changes in this case can destroy our mode shape correlation very quickly. So actually the only range for which the stiffnesses can be ideally updated in an automatic way is in between, where we have high sensitivity, and so where we can use an optimization tool to find what is an optimal spring stiffness. So in this case, it was tried, but was not leading to satisfactory results because of this phenomenon that we said, well, before using springs as an updating parameter, we need better understanding of which springs should be included, whether the initial value of those springs is already acceptable. I mean, if it's very rigid and it should be loose, or vice versa, I think those changes should be made in a manual way first, and the updating or the automated updating is only used for fine-tuning the spring stiffness. So therefore, we chose another strategy by introducing the stiffness scale factor as the updating parameter. So the stiffness scale factor is a scale factor to the elasticity matrix of an element. So this is a very efficient parameter for exploration because it can be used with every element type. It can be used with beams, with springs, with plates, with solids. And if it's also isotropic, non-isotropic materials, like we have also in this structure, we have some composite materials. So, and for isotropic materials, for example, the scale factor, which we use the label D for it, actually is equal to the elastic modulus. So that is ideal parameter for exploration because we can easily select it for all the elements. Now, in this case, if I would do that, I would be close to 1 million parameters. So this was tried, and I will have some results coming up. But for more practical working, we used existing element sets. So we have 89 element sets, and then we have a scale factor for each element set, and we have 5 frequencies to start with. And so here you see the kind of result that we look at. Clearly for the panel mode, we see is high sensitivity. For the tank, we see high sensitivity at the base. And for the global modes, we see high sensitivity at the support plate at the base, the satellite. We can look also in terms of a matrix. As you can see here, we see something really sticks out, and it's actually for mode number 3, which is the local panel mode, which is this red part is actually visible in the matrix with this high sensitivity value. And also as curves, we can look at each response, we can sum them. So there are several ways to look at the results. So we started updating the structure with these 89 parameters. But okay, if you see the curve here, we have quite a number of parameters for which the sensitivity, the total sensitivity is very small. So those were eliminated, and we only kept 51 parameters. Using 5 iterations, we see that we have almost complete convergence. We have parameter changes up to 120% of this scale factor. We see here the color coding of areas where we need change, the base, the panel in the back, clearly the base plate, and some other parts that need big changes. And with these changes, we see that our targets are satisfied. I mean, in terms of frequency, we go down to almost 0% difference in the frequency. It's visualized in the curve. In terms of MAC, there is not so much change because the parameters are global scale factors, and so I mean there is not much flexibility to change the mode shapes themselves. So now this was repeated in a second round with local stiffness parameters. So instead of using 51 sets, as was used here, now for every element in those inside those sets, we introduce a parameter, and this leads to 790,000 parameters. And now we have, of course, color plots where we can highlight the areas that need change, and it's probably not a big surprise that they are coinciding with some of the springs. So now you can decide whether to keep this global result as a final result. It's possible. It's a more mathematical model now. If you use this result, you can say, well, I'm going to use this information and actually make changes to the springs in those areas so that I do not have to touch the parts themselves, but only the joints, which are highly uncertain. Now, you can think that using 790 parameters, it's huge computation time. No, we're talking for 5 iterations, we're talking about something like 2 hours computation time in total. Which means five iterations. So confronting this result with background information that was available from the customer, it was demonstrated that actually the joints between the solar panel and the payload panel actually need to be revised. So this is the area that you see here highlighted, and by then inspecting the model, it was found that the rotational stiffness had to be significantly increased, but also that there was a mistake in the definition of the local coordinate system for the C-bush. They were pointing to a rectangular system, which actually it should be a cylindrical one for the correct interpretation of the rotational spring stiffness. So by making these changes, the 72 Hertz value that is almost 72 Hertz was reached by making those changes. And then there are other changes that result from verification, like the stiffness of the load cells, the Young's modulus that had been slightly increased, and also some spring stiffness, rotational stiffness that need to be increased because some part was considered free, a hinge that was considered free, but it actually was blocked, and therefore the rotational stiffness was modified from 0 to 1E10. We evaluated those changes, but they have only minor neglectable influence on the correlation. So it means we already identify the necessary change. It was caused by mistake, and where the updating has pointed to it. For